going back there, start recording, and okay, we started working on example 4.17 in the previous class. And I hope we worked out on the last part. Did we do that? Did we do V pi peak is limited to 5 millivolt? What is the corresponding value of V signal peak and V naught peak? Did we do it?
Yes, we did.
We did it.
Yes.
Okay. Now we are going to next problem, that is exercise 4.42. This is slight modification from previous problem. To improve the input impedance of example 4.17, the designer has reduced the bias current. That means bias current was 1 milliampere. Reduce the bias current to half of its original value. That means we have collector current 0.5 milliampere. I'm writing down the data, then I'll share the video. And hence increase the fraction of V signal that appears at input of the amplifier. In order to maintain the voltage gain, the value of RC is doubled. RC in the new case is, previously it was 5 kilo ohm, now it is 10 kilo ohm. Your R signal and RL remains at 5 kilo ohm. And beta is 100. And VA is 100. Now I'm trying to set the camera for you. So we have the same amplifier with a VCC and RC now 10 kilo ohm. Emitter is connected to ground. We have V signal and R signal. That is 5K. And we have an RL, also 5K. That is where we find V naught. And start with all the assumption. Okay, let's find the small signal values first. IC 0.5 milliampere. Now you can find GM is IC over VT. 0.5 milliampere over 25 millivolt. What's the answer? Somebody please confirm it.
Yes, sir.
Then we have R pi. R pi is VT times beta over IC. That is 25 millivolt times 100 divided by 0.5 milliampere. Answer is okay. If I have to go into recording, I have to close everything. Okay, we have start recording, and now I need to go and find the camera. Good. So we got R pi 5K. Now I can give you a clue. The clue is how I got these answers very quickly. IC equals 1 milliampere. Beta equals 100. Your GM will be 40 milliampere per volt. And your R pi will be 2.5K. If you remember, IC 1 milliampere, beta 100, GM will be 40 milliampere per volt, and R pi will be 2.5K. Now, what happened here is IC is reduced. IC is reduced to half a milliampere. So your GM will be reduced by half and R pi will be doubled. Okay, if you want to accept it, accept it. If you don't want it, don't do it. It's not that. If you remember in this way, your calculation can go very quick. This is a shortcut. If you want, take it. If you don't want, leave it. Now, we are going to do the small signal assumptions. Small signal assumptions are all battery voltages grounded. Number one. Number two is all capacitor act as short circuit for or at signal frequencies. Basically, that means grounded, capacitor is shorted. So with the help of two assumptions, we can make the small signal model. We start with V signal. That is your R signal, that is 5K. Oh, by the way, we did not work out small signal value. Oh, we did it. There is only one, that is we got GM and we got R pi. We did not find R naught. R naught is VA over IC. It's 100 over 0.5. You get 200 kilo ohm. Okay. Between base and emitter, we have R pi. R pi is currently it is 5 kilo ohm, and we have V pi across R pi, and emitter is connected to ground. There is your collector. Between collector and the emitter, there is a current. That is our small signal current, GM-VBE. We call it mostly GM-V pi. Now at the collector, we have R naught going to ground, RC is 10K going to ground, then RL 5K going to ground. This is R naught, which is 200K. From the same point, we have RC also going to ground, which is 10K. Then we have RL also going to ground. RL is 5K. Then we have V naught across parallel combination of R naught, RC and RL. Because all the three are parallel, we are going to work out RL prime is 200K parallel, 10K parallel, 5K. Someone calculate it for me. I'm waiting for. Yes, please. How much?
3.2.
You can't hear.
3.28K.
That is RL prime. Now, remember, your amplifier is beginning at that point. Amplifier is ending at that point. So, your input impedance is R pi, which is 5 kilo ohm. And your output impedance is like that. That is R naught, that is 200K parallel, R naught parallel RC, that is 10K. Is there an answer for that?
$9.5.
So we have output impedance, we already have input impedance. What is next? We can work out the gain of this amplifier, that is AV. AV is minus GM RL prime. GM is 20 milliampere per volt with a negative sign times RL prime. We already have 3.28K. How much? Okay. 65.6 ohms. How do you get ohms for a voltage gain? So for this problem, voltage gain actually reduced. We had voltage gain 97.56 yesterday for the first part of the problem. Oh, sorry, 4.17. Why the voltage gain reduced? This is the reason. GM became half. Why GM became half? Because IC reduced into half and RC was increased. RC was 5 kilo ohm. Now we are working with 10 kilo ohm. But remember, when we find RL prime, only one value, 10 kilo ohm, is doubled. R naught doubled, but that is too big value for a parallel combination. Your RL remains at 5K. So there is a small increment in RL prime to pick the voltage gain up. So we have a reduced voltage gain. Now, second part of the problem. If V pi peak equals 5 millivolt, V pi peak. Find corresponding values of Vs peak and V naught peak. Because all are in peak, you don't have to change anything. What you need to do here is make an expression for V pi. V pi peak equals 5 millivolt equals Vs peak divided by Rs plus Ri times Ri. This is Vs peak times Ri is 5K divided by 5K plus 5K, 10K. From here, we can find Vs peak equals 5 millivolt times 10 over 5. That is going to be 10 millivolt. In yesterday's problem, here, when V pi was Vs divided by 3. And today, your V pi is half of Vs. Or in other words, your amplifier is seeing more voltage. at the input. Remember, V pi is the voltage seen by the amplifier. V signal is what we supply to the amp. Then we need to continue the problem and try to calculate GB. GB is AV times Ri over Rs plus Ri. AV we already have now 65.6, input impedance 5K, Rs plus input impedance is 10. So your answer will be somebody please confirm.
Correct.
So we got GB as well. Time for questions. Okay, now we are moving forward and we are going to apply a common emitter amplifier in voltage divider bias. If you have a voltage divider bias, remember we have done analysis of a voltage divider bias while we did BJTs at DC. RC, RE, R1, R2, R signal, CC1, CC2, CC stands for coupling capacitor. And at the emitter, there is an extra capacitance. We call it CE. This is emitter bypass capacitor. Okay, we will study about use of CC1, CC2, and CE at a later stage. CC1 and CC2 are to block the DC and bypass the AC. Emitter bypass capacitor. Remember, once you do the small signal model, signal current reaches here and capacitor acts as a short circuit to the ground. So in the small signal model, RE is bypassed. So we will not see RE at all. Now, we recapture a little bit of things that we did in our BJTs at DC now. To analyze, if you want to do a small signal analysis, number one thing that you need is your collector current. Currently, in this kind of a bias, collector current value is not given. So we go for DC analysis. Basically, it is first you find VBB. That is Thevenin voltage at that point. Then we also find Thevenin resistance exactly at the same point. RB is R1 parallel R2. Then we can make an expression IE approximately equal to IC equals VBB minus VBE over RB over beta plus 1 plus that is from Thevenin theorem. We have done this kind of analysis while we did BJTs at DC. Now you can see whatever we learned before is coming back again. That also says something. If you forget what you did before, then you will be stuck again. Now we found IC. Once you find IC, we know what to do. That is small signal analysis. First, from IC, you find GM. Then you find R pi. Then we are going to find RL prime. Then we also find R naught. What is next? We make a small signal equivalent diagram. To do that, we have two assumptions. Ground, battery connections. Or capacitor, short. Basically, we are going to end up having for one small signal analysis. There is only one battery, that is VCC, grounded. Capacitor CC1, short circuited. Capacitor CC2, short circuited. Capacitor CE, shorted. Now, from Vs through Rs, signal current flow and reach at that point. From this point, you have R1 going to ground, R2 going to ground, or basically R1 parallel, R2 going to ground. We can even say RB going to ground. This is base. Between base and emitter, tell me what you have between base and emitter. Somebody must say it. What is there between base and emitter? Can someone say it? What is between base and emitter? I am talking about small signal model. There is an input resistance looking at the base. Tell me the name of it.
R pi.
There is an R pi between base and emitter. You reach the emitter. From emitter, there is a short circuit going to ground. And tell me what is between collector to emitter. There is signal collector current flowing. From the collector, RC going to ground. From the collector, capacitor is shorted, RL going to ground. So with all these values, we can make a small signal diagram, V signal. And there is R signal. You reach the base. From the base, R1 parallel R2 going to ground. I call it RB. From the same base point, there is input resistance looking at the base. We call it R pi. Across R pi, there is a V pi. You reach emitter. At the emitter, there is a capacitor connected, and that capacitor acts as a short circuit. So emitter is connected to ground. And between collector and the emitter, there is signal collector current flowing. Signal collector current, we call it GM V pi. That point is collector. At the collector, we have RC and RL. If R naught is given, include that as well. Now, looking at the input, that is the amplifier beginning point. So, that is your input impedance. Looking at the output, there is your output resistance. Output resistance is RC. And if you are including R naught, then we simply say R naught parallel RC. Now, going back to the input. Input, you see between these 2 points, RB is in parallel with R pi. So your input impedance is going to be RB parallel R pi. So this is one of the difference that we see. Previously, we did not see RB because 2 problems that we worked out, there was no RB given. Now, if there is an RB, as now in a voltage divider bias, you will have an RB. You have to include that into your input impedance calculation. Once you get up to here, then basically AV is minus GM RL prime. Okay, we did not work out RL prime. RL prime equals R naught parallel RC parallel RL. Or basically anything at the collector, they all go parallel. Then you can work out your GV, that is going to be AV times RI over R signal plus RI. Time for questions. And all that are given on this slide. This is a recap from, especially the first part is a recap from BJTs at DC. VBB, RB, and IE nearly equal to IC. Then we have small signal values R pi, GM, and RL prime. Then we have the small signal model as we just now did on the paper. So the major difference is input impedance RB and R pi are going parallel. That's a major difference here. Okay, I still recommend that you pick up from the circuit diagram, small signal diagram, and work out accordingly. You need to remember all these BJTs at DC. There are 2 or 3 formulas that you need to remember. You need to remember R pi is VT times beta over IC, and GM is IC over VT. RL prime is total loading at the collector. You can easily pick it up from the small signal diagram. Okay, all these things, voltage gain, GMRL prime, and overall voltage gain is AV times RI over RS plus RI. All right, time for questions. All right, we are going to start.